Well, hi there and welcome back. We just looked at the idea of electrons and gained some basic ideas. So now let's have a bit more of a delve at this. And today we're going to look at how do electron clouds differ. Remember we got to the stage of looking at our current model of the electrons is a cloud or an area where we find them? Well, as we can see on these, we can see there are clouds here and they move away from the nucleus. Here is our nucleus in the middle, and for some reason we started calling them with the letter K, and then we went through the alphabet after that. So the second one is L and M and N and O and P and Q. And we have some really weird ideas about what parts of these clouds look like. And that links us to the idea of an orbital or part of a cloud. So I'm not trying to confuse you, hopefully, with this, but let's just have a look at it. So let's look at where we were and then build on it. Alright, last time we looked at this one, and we've come to the idea now, essentially our model is electrons move around the nucleus. Check, we're okay with that. Here is your nucleus. Electrons move in these areas. Electrons don't move like cars on a racing track or planets around the sun. They move randomly. Alright, so they're going to be found in these areas, but they're not found between them. Remember we said they're found in the area here or here, but not in the intervening areas. Alright. Electron, where we find them, is decided by how much energy that electron has. And we saw that the lower amounts of energy are found in here, electrons with lower energy here, electrons with higher energy are found here, and obviously the next layer out they'd be higher still. And last but not least, the electrons are different from each other, because if they had identical properties, that would mean they are an identical electron. Now this has all got to do with quantum mechanics and goodness knows what, so I'm not going to go into that. That has to be taken on trust. Sometimes we just have to follow our trust on this. Alright, so where's this going to lead to? So when we're going through it, now here's some interesting information which I'm going to let you read, but I'm going to sort of go through this as well. I've drawn this imaginary atom and I've got 1, 2, 3, 4 areas or clouds where the electrons could be. Notice that each cloud gets further and further away from the nucleus. So this means if I looked at the radius, right, we've got that is a small radius, that is bigger still, and that is bigger still. And we all know that if I've got a ball, and we're drawing these as circles, just for convenience sake at this stage, and it's easiest to make analogies that way. So if I've got a ball of this radius, of the first little arrow radius here, it is going to be a smaller ball than a one with a bigger radius, and it's going to be smaller than the one with bigger still, and smaller than the one with bigger still. So as our clouds form different distances away from the nucleus, it means that they start off being small and then get bigger and bigger and bigger. Now size does matter. As I've said up the top here, it's about having room. So if we've got a small circle, we haven't got much room to fit many electrons. If we've got a bigger circle, it means we can fit bigger electrons, or bigger cloud, we can fit bigger electrons. If we've got a bigger cloud again, we can fit more electrons again. And if we've got a huge cloud out the outside, we can fit a lot more. Okay? So we've gone through the idea of trying to work out how all this happens, and in a later video I'm going to ease this out a bit by showing you the periodic table. Now the secrets of the periodic table are very easy to understand. Alright, the periodic table, believe it or not, the current one you're going to use in your tests is based upon how the electrons are packed inside of it. of the atoms. Right, so scientists then deduced that the number of electrons in any shell would be equal to this expression, 2n squared, where n is the number of the shell. So if we come into this one, which is our first shell, so that would be 2 times 1 squared, or 2. So this first one has 2, that's where that comes from. So just to write that down for those who are not really happy, 2 equals 2 times 1 squared. Right, let's look at the next shell. The next shell is number 2. So that's going to be equal to 2 times 2 squared. Now, 2 times 2, or 2 squared, is 4. And multiply that by 2 is 8. That's where the 8 comes from. The third one is 2 times 3 squared, which is 2 times 9, or 18. So that's the maximum number of electrons I can fit in the third shell. I hope this is becoming a little bit obvious now. Alright, so all this matters with it. Now I'm going to introduce one more term here, and I'm going to do it now because we're going to find out about it later on. The outermost electron cloud that has any electrons in it, it must have electrons in it, is called your valence cloud, or valence shell. Some people call it shells, other people call it clouds. It's pretty much the same sort of thing. Alright, so if I've got this one with only 2 spaces for 2 electrons, then it's pretty tight. Alright? There's not much else we can have there. But obviously a bigger electron cloud that can hold 8 means there could be parts within clouds. We know when we look at the sky and see clouds, not all clouds are the same. The bigger clouds have more space in them than the smaller clouds. This is going to come back to us. Alright? So we can look later on, and I haven't done it yet, and I'm not doing it today. We can look at how the natural elements from hydrogen to uranium have between 1 electron or 92 electrons. And there is a way that they pack those electrons into these clouds. And it's based upon this, and it's based upon what I'm going to show you next. Alright, normally in MYP, or middle years program chemistry, this is about as deep as we need to go, this thing here. But let's have a quick look. Let's just extend ourselves. Right, within the cloud, within these big clouds, as clouds get bigger, there can be more sub-areas. So we could call these subshells or subclouds. And what we actually find is that in small clouds, only this subcloud appears. As clouds get bigger, then we include other ones. So if you like, in our first shell, or K orbital, we only see this. Because the next shell out, which is called the L shell, or the L cloud, we see those two. Now obviously the next one out is, and you're seeing the pattern here now, the next one out is LM cloud. It's bigger, it's the third cloud out. It can fit this, it's got 3 sub-energy levels. Now remember, each one of these levels has got its own amount of energy. The S shell, you need less energy to live there than you do to live in the P shell. You need less energy in the P shell than you do to live in the D shell. And then of course we get this last one out here called the F. Now I haven't looked lately why they have named them this, and I'm not really interested in it. The fact that we have these sub-levels, and they're called S, P, D and F, is the important part. And each of those can hold a certain number of electrons. And that helps us work out how they're going to fit together. Now that's going to be the subject of a subsequent, the subsequent little lesson we're going to have about how they actually fit in these things. All right. So these sublayers of subshells, they are there. And don't forget, it's all about least to more energy. And I'm going to stop it there because it doesn't require us to do any much more than this for our tests and exams.